How's it going, Calc kids? I'm back again to teach you guys some more calculus inside my lovely classroom. You can see I have not changed. Okay, today we are going to do a 3.6 fuzzy chain rule. This rule is off the chain. Sorry about that. Okay, here is the actual chain rule. It says that if you have a composite of functions that is differentiable at x, then your It says that your f prime of g of x times g prime of x. What? Okay, let's say you have two functions, right? Let's say you have sine 5t minus 3. Okay. Moby. For this one, your f of x is your outer function, it's your sine. Okay. Your g sub x, I should use t, it's 5t minus 3. Because then when you take the composition, it's a function inside of a function. Okay, so what this says is my f prime, which would be negative cosine. I'm sorry, not negative cosine, just good old-fashioned cosine. I just taught this lesson. Ooh. And then I plug in my g sub x into here. And I times it by my derivative of g of x, which is just good old 5. Why is this lagging so bad? And that would be my derivative. I'll call it y prime, just for fun, if this was my y. Okay? I gotta figure out what's going on here. Hey, yeah! We'll have to make it through. So, anyway, that's the technical definition way. I'm going to tell you the way I remember how to do this stuff. Okay. I just did it. I like to refer to it as the outside-inside rule. Okay? What that says is if you have a function of a function, then your derivative is the derivative of the outside times the derivative of the inside. Derivative of the outside times derivative of the inside. Outside, inside. And you just, let's take a look at an example. Okay, so differentiate cosine of 3x to the fourth minus 2 with respect to x. Okay, our inside is the function inside of the function. That's our inside. Okay? So when we take the derivative, first we take the derivative of the outside. Our outside's cosine, that derivative's negative sine. Then we leave the inside alone. Let it be. Just leave it alone, guys. Okay. The derivative of my inside is 12x to the third. Then I times it by that at the end, and that's my answer. You guys want to see another one? I'm gonna make one up right now. If it works, oh, my mouse works. Suppose you had to do. I lost it. I'm back, kind of. Alright, so suppose I'd find derivative of this. My outside is the tangent, and this is on the inside, right? Derivative of tangent, you may all remember, is secant squared. Now we leave that inside alone. And we times it by the derivative of my inside. 4 times 3 is 12, x squared. That's all the chain rule is, guys. Derivative of the outside times derivative of the inside. Outside, inside, outside, inside. Da, da, da. Can you even... What is that pointing? Where were you pointing? Let's try the chain rule on a tougher problem. Look at this beast. How are we going to do it? It's a rule inside of a rule inside of a rule with many rules. First, we'll make this so it's y equals sine of x squared to the 1/3, because that's what cube root means. Okay. Not even on the right notes. Yeah. So now, first things first, derivative of my outside. So I bring the 1/3 out in front. In fact, let's do this. So you can see all the functions inside of a function. Subtract 1 from 1/3 and you get negative 2/3. Next, I'm going to need to times it by the derivative of the inside. Okay? Which is sine of x squared. Derivative of sine is cosine. Right? And again, we're going to leave that inside alone. But now we have to times it by the derivative of the inside again. The derivative of x squared is 2x. Do you see the chain? You just keep taking the derivatives of the pieces until you're done. Because there's no inside part to this. Okay? And that's our answer. Well, if you really want to write out, it'd be 2/3 x sine that's not really, I would take this. I would take that. Okay? A parametrized curve is one where your x of t and you have a y of t, so you have a particle that's moving in respects of time all over in 2 dimensions, and you want to find out what's going on. Okay? Let's see what the next thing is. Okay? In order to do this, dy over dx is your derivative you're used to. So if we find the derivative of y with respects of t and the derivative of x with respects to t, you can divide these, okay? Your t's cancel and you're left with dy over dx. Crazy! Oopsie schnoodle. Let's try one. Suppose x equals t squared and y equals sine of t. And we want to find dy of dx. Derivative of y with respect to x. Okay? Better yet, let's find the tangent line at t equals pi. Okay? So first I need to find the slope of my line at that point. So I need to find my dx, my derivative of x with respect to t. Well, I'll bring the 2 out in front. Bingo. Next I need to find my dy over dt. Derivative of sine is cosine. Okay? What slope? Is it your change in y over your change in x? Yeah. So I put my change in y on top, all over my change in x. Okay? So that's my derivative. That's my dy over dx. Okay? Now I plug in pi. Oops. Okay? So I get cosine of pi all over 2 pi. Cosine of pi, please someone tell me out there you know how to do it. With your unit circle, cosine is your x coordinate, and at pi you are at -1, right? So there you go, -1 over 2 pi is your slope. Now you set up your equation. Y minus your y equals your slope times x minus your x, right? Your slope is negative 1 over 2 pi from up here. Now, to find your y coordinate, you plug in t equals pi into your y equation. Sine of pi is 0. Okay? For your x, you take t equals pi and you plug it into your x equation. So you get pi squared. Okay? So actually, that goes away. Y equals, distribute that through just for fun. Negative x over 2 pi minus pi squared over 2 pi plus, because the negative has to go through. So it's actually pi over 2. And that's your equation. That's where I'm going to end it, guys. I hope you enjoyed this as much as I did. Bye-bye.